So we are very happy that Eduardo has agreed to be the first guest speaker to this ARIVE series. So special honor, and we are very happy. He has done a lot of work on eye tracking, attentive interfaces, and he agreed to talk to us today about that. And with this, I'll just hand over to Eduardo. We are very excited.
Thank you very much for the invitation to join your seminar series. I watched a few of the talks online, and it's a lot of interesting stuff happening. So I'm honored to be invited to share some of our work with you guys. So today we're going to be talking about attentive mixed reality systems. So I'm going to be the focus will be on mixed reality, but I'm also going to show a few bits and bobs that I've done in the past involving attention and eye tracking in other platforms as well. So I'm calling in from Melbourne, the most locked down city in the world. This is what I used to look like when I could actually go to a hairdresser. But I'm a senior lecturer at the University of Melbourne, and until the end of the year, I'm also a ARC DECRA fellow from the Research Council here in Australia. I'm at the School of Computer Information Systems, where I teach subjects on interaction design and web development. So today's talk will be about how can we design mixed reality systems that respond to our attention. So attention will be a core topic of today's talk, and I'm going to be discussing attention from three different perspectives. So first, as a phenomenon to be understood, so how does mixed reality affect our attentional patterns? Then as a psychological construct to be sensed, so if attention matters, how can we make estimates and inferences about users' attention? And finally, as a design material for interactive systems. So if we can sense this information, so what? What can we do with it? How can we incorporate that information into the interaction? So let's begin by discussing what is attention. So there is not a single universal definition of attention, as with many other things. William James called it the withdrawal from some things in order to deal effectively with other things. Schifrin said, all the aspects of cognition that the subject can control. So things that you have conscious, deliberate control over. So, and to all aspects of cognition having to do with limited resources or capacity and methods of dealing with such constraints. And the American Psychological Association defines it as a state of focused awareness on a subset of the available perceptual information. So what all of these definitions share is that, our perception is capturing information from all over the place, and attention is what helps us focus on a subset of all of that stimulus. So it is about making decisions about what you're going to process effectively and what you're not. So why does it matter in mixed reality systems? So I'm going to start with a case study of a paper that we presented at ISMA a couple of years ago, and this was an installation that a local mixed reality development team in Melbourne here called Foria built in partnership with Netflix, the WWF, and there was another partner. I can't remember who it was, but anyway, they were hired to develop this really fantastic app that was meant to be deployed in museums. So this was the app. This was linked with Netflix's documentary from the latest one from David Attenborough, and the idea there was that the installation would combine a massive panoramic screen in the back that you can see here. Let me see if I can draw. Yeah, here. And each user would use a mobile phone like this that would use these patterns on the floor to track the space. And they wanted to create a social experience. So you'd have a bunch of users like this moving around the space, interacting with the application in mixed reality, while also consuming information from the big display. So sociality was a core element of the experience that they wanted to design. And we partnered with them to do a study on how people interacted with it. So this is a new kind of platform. There's a lot of stuff happening. It's multimodal. You have a conventional screen, you have audio, you have the app, you have the interaction with the space. So the basic premise of the app was that you find a certain ecosystem, and as you walked around, the ecosystem was would slowly deteriorate, and you could use the application to rewild that ecosystem. And this was deployed in 3 spaces around the world, in the UK, in Singapore, and in New York. And we visited 2 of them to do this in situ research. This was mostly an observational study where our team sat there and watched people interacting with this, and later on interviewed 45 groups of visitors to see how does this interaction work in a naturalistic environment. So this was the first study of one of my PhD students as part of his PhD that is all about attention in mixed reality. And we wanted to start, rather than starting with a controlled experiment, we wanted to go in the wild and see what these behaviors are like in a naturalistic setting. And we found a few tensions in this user experience, right? So first, you have this split attention effect, which, you have a lot of stimulus coming in. So you had the big screen, you had the application, and what we found is that users were basically ignoring this really flashy, beautiful David Attenborough documentary that was playing there, and only focusing on the augmented reality app that they had on the phone. And also, even though the experience was designed to be social, that aspect mostly failed because people were so focused on interacting with the augmented reality. So you had this attention tunneling effect where people just focus on the virtual content and ignore everything else. So there was less social interaction, there was less engagement with the content. And one unexpected finding from this study was that the docent, which is the person at the museum that is responsible for coordinate the activities, became really important for the experience to work. And in the paper, we describe the different roles that the docent plays to support the interaction with the app. As a guide, as an interpreter, kind of in a sense, conveying the information that the installation was meant to convey, as tech support, because this technology is very feeble, it breaks, as a social facilitator to actually try to facilitate that social interaction the app was designed to foster, and also as a performer, as a storyteller, and so on. And in the paper, there's more detail about this. So this was presented at ISMAR in 2020, and we were really interested in this attentional tunneling phenomenon, where formally this is defined as when users focus excessively on the virtual content while neglecting the physical surroundings. And this is a concept that emerged from early augmented reality papers, mostly from defense in pilots, in head-up displays in aircraft. So, and there's a bunch of papers and articles reporting the risk of augmented reality applications that speak to this attentional tunneling effect, right? So people neglect critical events, neglect objects. It might cause hazards during walking, biking, and driving. All of that commotion that happened when Pokemon Go was first released is a great example of that. And our own experience in watching people use these scenarios, these applications in a naturalistic setting. And we went in the literature and tried to identify what is it that causes this attentional tunneling effect. And the literature so far had suggested that this might be caused by the presence of 3D content by itself. So it's fancy graphics, drop users' attention, they focus on that and forget everything else, right? But we didn't think that was quite right. So we hypothesized that the associated task to the virtual content was actually what was causing that attentional tunneling effect rather than the virtual content itself. And this hypothesis was based on previous research in psychology on a related phenomenon called inattentional blindness, where users engaged with a task tend to miss events and objects, even when these events are directly within their foveal vision, meaning their eyes are pointing at it, but they're still not perceiving anything. And this was, there's this classic study of the gorilla, you probably know this one, where you have this scenario where there's a bunch of people throwing basketball balls to each other, and the task of the user is to count the number of passes, and there's this gorilla that walks past. And if you're counting the passes, you don't see it. If you don't have that task, everyone notices the gorilla, no problem. So we wanted to create an equivalent experiment that could help us tease out the effects of the 3D graphics and the effects of the task associated to the 3D graphics. So we designed this study where we asked participants to use a mobile phone, the Augmented Reality app, and there were cubes floating around, passing a ball to each other. And there would be LEDs that would randomly light up. And whenever they saw one of these LEDs light up, they had to click a button. And we wanted to what we noticed in the previous literature was that in these experiments on attentional tunneling, the condition where with the virtual graphics would always have an associated task, and the condition without the virtual graphics wouldn't have any task, which is what we believed explained there was a confound there between task and graphics. So we wanted to tease those out. So we had two independent variables. So the event type, whether the LEDs were virtual, meaning they were in the plane of the phone, or they were physical, meaning physical LEDs on the environment, and the content type. So there was nothing, we're just seeing the feed of the camera versus having the blocks moving around, but you don't have to do anything about the blocks. And having the blocks plus you have to count the number of passes in the same situation as the gorilla. And we were measuring reaction time for each of these LED blinking events. So this is what the task looked like. So we made sure that there was plenty of clutter behind the screen, so that there was, this was not so easy. And you can see the LEDs here. So there were, oh, sorry, let me just turn on the pen again. Okay, so you can see here the LEDs mounted around the environment, and they would randomly light up, and the user had to click a button. And what we found supported our hypothesis, right? So when you didn't have any associated task with the condition, meaning participants didn't have to explicitly count the number of passes, there was no difference between the reaction times. So we did an equivalence test there to see, because we predicted that they would be the same, and there was no significant difference there. But when we added the task, there was a strong effect there of the task on the reaction time. And later on, we replicate, and you can also see a small difference in the reaction time between the physical and virtual LEDs. And later on, we conducted a second test just on Mechanical Turk, just with a 2D interface or web-based without any augmented reality, because we believed that the reason why the physical LEDs were led to faster reaction times was because of peripheral vision. So we did a follow-up study where we removed that peripheral vision, and they were the same. So the takeaways from these studies is that the display of virtual content alone is not likely to be the cause of attentional tunneling in AR. Attentional tunneling in AR is more likely to be caused by the task associated to the virtual content than by the simple display of the graphics. And peripheral visibility of physical content minimizes this effect of attentional tunneling, because you're also paying attention to what's happening outside the display. So we published this at CHI this year. Now I want to talk a bit about this, how can we sense attention, right? So that's the first component there was understanding attention as a scientific phenomenon. Now I want to move on to how can we capture users' attention. So I've done a lot of work on eye tracking, and gaze is a fantastic way of trying to estimate users' attention. And that's because gaze signals interest, right? We all look at what's interesting, at what's relevant. We look at what requires our attention. And we can't look at everything at the same time. So gaze can help us distinguish what is at the forefront of our attention. Remember, I started this talk by talking about how attention is about focusing on some things and not on other things. So because our eyes can't point at everything at the same time, they give us this hint at exactly what is it that we're processing. Of course, gaze is not the same as attention. Just because someone is looking at a certain thing doesn't mean that they're paying attention to that thing. So for example, this guy here is not really trying to look at the ceiling. He might be just trying to recall something. And in these situations where the gaze direction doesn't match what's the focus of our attention, we call it covert attention. So even though attention and gaze direction are not the same thing, gaze offers a pretty good estimate for the attention point, and in certain circumstances, this assumption can be very useful. Now, gaze is a natural pointer. So most computer interfaces are built for pointing, largely because we look at what interests us. These systems can use this gaze information as a selection mechanism. The key thing here is that, you know, this has been used as a assistive input modality for disabled participants for a very long time. There's been a lot of work on gaze pointing for interaction for people with ALS, for example, but this is not really what my research on gaze input covers. I'm more interested in the using gaze as an additional input modality for any kind of user. So our eyes are constantly jumping between, so they spend most of the time doing two kinds of eye movements. So they're called fixations, which is when your eyes stop somewhere, and saccades, which is when they jump. So our eyes make this very jerky movement, and they're constantly moving. So if our eyes are rarely still, this creates a challenge for gaze pointing. So even though it is very natural to point at something with your eyes, it's really unnatural to point and keep your eyes pointed at something. So the solution that we envision here is multimodal interaction. So I've done several projects using gaze as one of the modalities in a multimodal interaction system, but I'm going to talk a bit about the latest one, which we published at CHI this year, which was the work of Difeng Yu, one of my PhD students. So here we were looking at gaze-supported interaction techniques for 3D object manipulation. So the idea here is to explore this design space where gaze is pointing and the hands are manipulating. So you can read the details in the paper, but we have an iterative design cycle here where we started with a few alternatives, ran several experiments comparing them and iterated over them. And in the end, we designed a smaller set of techniques. But so in this one, for example, this is one that I quite like because it builds upon this jerky movement of the eyes, this imprecision in gaze pointing. So when you move your eyes towards a certain object, there is this kind of fuzzy region around the object within which the eyes are the pointer, but outside of which, if your hands are within that region, the hands are manipulating the object, but when you look away from that region, the eyes push the object. So there's some interesting discussions around how can we leverage the speed and naturalness of the eye movements with the precision and accuracy of the hand movements for manipulating the object. So, and in general, the eyes shine when there's a long distance to be traversed, right? So if you're talking about smaller distances, hand manipulation tends to do a pretty good job. So the inaccuracies of the eyes really create more problems than they solve. But when you're talking about moving objects across large distances, then the eyes really shine. Now, I've told you that our eyes spend most of the time alternating between saccades and fixations, but there is another eye movement that our eyes also make called smooth pursuits. So this is not a jerky movement in contrast with the previous ones. So smooth pursuits only happen when we're following a moving object. And what's interesting about them is that our eyes are not able to make smooth paths. So if you try to force yourself to make a circle with your eyes, you just can't. You know, you can make a polygon, but your eyes are not able to make a full circle unless you are following a moving object. So if I look at this pen and move this pen, not a problem. Your eyes can make that movement, but only if you have that moving stimulus. And so imagine that you have an application where with a non-calibrated eye tracker. So your eyes are looking somewhere. Because you don't have any calibration, you don't know where the user is looking. The eyes are jumping, so it's a very noisy signal. So this one is animated with PowerPoint, but it's not too different to what you might find in real eye tracking data. So, you know, if you see noisy data like this, there's no way of telling which of these targets the user is looking at. But if we get these targets to move, all of a sudden, it's pretty clear which one the user is looking at, even though there is an offset between these two, the gaze point and the target. And this offset might also be in scale, right? So the circle where the eye movement is traversing is much smaller than the other circle, and it could be completely offset from this. So this correlation between the movement of the eyes and the movement of the objects gives us an intuition about which object the user is likely to follow. And because we can't fake these movements, it gives us a lot of information about what the user is trying to do. And we've explored this concept in several input modalities. So probably the most successful one was this paper called Orbits, which we published at WIST in 2015, where we showed that we can use this technique to enable gaze interaction in smartwatches. And we developed a bunch of application demonstrators where, you know, for example, here you receive the call, there's this little target that's moving around the circle, you follow that target, it summons other targets, and you can proceed the interaction like this very naturally. And because it's natural for eyes to follow something that is moving, you know, this actually flows quite nicely when you're actually using it. So it's very natural to follow something that is moving. So we published this originally in 2015, and since then, I've spent quite a lot of time thinking about this, about motion correlation, not just as an interaction technique for eye trackers, but as a fundamental principle for interaction. So in the same way that pointing is a paradigm, or a repertoire of symbolic gestures is a paradigm, I believe the motion correlation is also a unique paradigm that's quite distinct from these other paradigms, where it's not only the shape of the gesture that matters, but also how in sync that gesture is with another stimulus. So the main principle of motion correlation is that if each target moves in a unique way, the user can express the intention to select a given target by matching its movement with the input device. And this is very generic. You can do this with the eyes, you can do this with the hands. I've seen this done with the heads, and there's a lot of papers out there that have expanded on this principle in several input modalities and contexts, and including mixed reality. So Augusto Esteves, who is the co-author of the Orbits paper, you know, he's done this with the HoloLens and so on. And I expanded a few of these ideas. So if you're interested in finding out more about this as a principle, we have this Tokai article that we published in 2017. And this year at CHI, I also published one where I take an even more formal approach based on information theory to try to understand how is it that these techniques work. So the takeaways from this segment are that gaze direction offers a reasonable estimate of users' attention, but this is not necessarily the case. With a calibrated eye tracker, we can just use gaze direction as a pointer. And indeed, pointing with the eyes is natural, it's quick, but it involves several inaccuracies that are inherent to the saccadic movement of eye movement. So if you're thinking about gaze pointing, you can't really design interactions in the same way that you're designing interactions for hand pointing or even mouse pointing. You really need to think hard about this jerky nature of the eyes. And we can circumvent the need for calibration using motion correlation-based techniques. So they don't require any kind of calibration. You can, the most basic technique for doing this is just using Pearson's correlation. And since then, we've developed other algorithms that work better than Pearson's correlation. But if you just want to give it a try, you know, basic Pearson correlations on the coordinates of the targets and the coordinates of the gaze point will already give you some really impressive results without any need for calibration with any kind of input modality. So what else can the knowledge of the user attention offer? So eye movements reflect context, right? So our eyes are not they're not stem from inside us and do whatever we want them to do. They also respond to the visual stimulus in front of us. So our eyes, our brains are always, it's a bit of a pull and push between what is in front of us and how they draw our attention, but also what we want to accomplish given the stimulus. And the seminal work that demonstrated this was done by Alfred Yabus, which was a Russian scientist. And in this famous work, he showed participants this painting called The Unexpected Visitor. And he recorded gaze data using a really old school eye tracker that looked more like a torture device. But there was a twist. So participants were given different tasks to think about when they're observing the image. And as you can see here in his results, if you don't tell them anything, if you just let them examine the scene freely, the eyes are just scanning everything, they're paying attention to everything. It's a bit of undirected. So it's really driven by the features of the scene. It's really the contrast, the faces, and so on. Whereas if you ask, for example, give the ages of the people, you see this pattern, right? It's really focused on the faces of the people in the painting here. So you can really see how by giving someone a task, it completely changes their movement. So if the task leads to different eye movements, then perhaps we can do the reverse. And by monitoring eye movements, we can discover the task. Myself and others, including one of my PhD supervisors, Andreas Bulling, have done a lot of work on activity recognition from gaze data. The most recent that I've done was this paper where you collected a big data set, and this is available if you ever want to play around with activity recognition for gaze data. We're happy to share that. But we collected a big data set of a bunch of people playing different video games, reading different pieces of text, doing different programming activities, browsing the web, and so on. And we collected that data set, and we discussed the role of different features in how they reveal different activities. So we can, if you're interested, get in touch, and I can send you this data set if you're ever interested in doing this. But the point here is, just by looking at the eye movements, without looking at the stimulus, we can actually infer what the user is doing. And others have shown that you can infer, for example, social situations. Are you talking to someone, or are you by yourself? You can discover whether someone is outside or inside, or they're stressed or they're not. So there's a lot of contextual features that you can pick up from gaze data, which is quite cool. Now, attention is not just about activity. And also it's not just about where your eyes are pointing. We started thinking about what can we use this data to understand to kind of give a bit more meaning to the different kinds of attentional states that one can be in. So we started looking into the attention literature, and we found this distinction between different kinds of attention. So sustained attention is when you're just paying attention at one thing at any point. So I hope that during this talk, you're paying sustained attention to my speech and my slides, right? But perhaps you are doing something else. You are flipping back and forth between this talk and that email that you had to respond. So you're in alternating attention. So you're jumping back and forth between two tasks. Perhaps you are listening to me speak during, maybe you're outdoors, you're in a cafe, in a restaurant, and there's background noise, and you're trying to block out all of that and just pay attention to me. Or perhaps you are just trying to pay attention to two things at the same time. Maybe you are attending another seminar at the same time as this, and you're trying to pay attention to both. So you're dividing your attention between these two states. So our hypothesis was that some of these have different cognitive demands on you, and they require different gaze patterns. Meaning, if we can detect if we can use eye tracking to detect where is the focus of your attention, perhaps we can use a different modality that estimates cognitive workload to be able to differentiate between these. And we've been playing a bit with facial thermal imaging. So the hypothesis here is that the harder whatever you're doing is, the more cognitive demand you have, the more blood flows up, and you see a shift in the blood flow towards towards your brain, and this can be detected with a thermal camera looking at your face. So basically, the more blood flows up, the higher the temperature is here, and the lower the temperature is here. So we've been playing a bit with this. So we collected this data set with different conditions, and you can see the conditions here. So we had conditions with audio stimulus, visual stimulus, audiovisual stimulus, and some controlled psychological tests. So we used the Stroop test at different levels of difficulty to try to kind of elicit some of these attentional states. And we trained a classifier that used gaze to try to classify them, used thermal imaging to try to classify them, and a combined classifier that did both. And you can see here a few of our results. And you can see that with gaze, we can know the locus of your attention, meaning alternating is very easy to detect because just see, okay, your attention is here, your attention is there, very easy. Gaze gives you a pretty good idea about that. Whereas cognitive workload through thermal imaging can give you, for example, whether you're paying attention at just one thing. The cognitive demand is much lower than, for example, if you're divided. So there's no question, if it's just between, are you dividing your attention or are you just paying attention to one thing, it's pretty clear here. There's no ambiguity there whatsoever. So as we hypothesized, we can use thermal imaging to detect cognitive workload. We can use gaze to detect the locus of attention. And when you combine them, you get a pretty good picture about your attentional states. There is some ambiguity between selective attention and divided attention, as you can see here, right? But this is likely to be because these are inherently difficult to tell apart. If you have two stimuli and either you're trying to block one out or you're paying attention to both at the same time, it's really difficult to actually have to be in just one of those. Even when you have background noise and you're trying to block that out, sometimes some of that flows through and you are actually paying attention to two things at the same time. So we were pretty happy with these results here, which are published at UBComp a couple of years ago. So, but this talk is about mixed reality, and so far I've been showing you a bunch of results on desktop applications. Can we do this in mixed reality? And we've played a bit with some potential for this. So we built a prototype using, of course, in mixed reality, your face is covered, so facial thermal imaging is a bit difficult to do. So we tried to do this with some temperature sensors here, so you can see the prototype that we created, and we even got to integrate that into a HoloLens. And we ran some studies, but these sensors are really cheap, so it didn't work as well as these thermal cameras that cost tens of thousands of dollars, right? So this is something you can buy very cheap for a few dollars online. But it still kind of works. It was difficult to detect the different levels of difficulty, but if all you want is a binary classification, are you in high workload, are you in low workload, that's pretty doable still with this approach. Some of you might be thinking about, well, if we can't use facial thermal imaging, maybe we can use EDA or GSR. Maybe all you need is a wristband or a smartwatch, something like that. Maybe you can use that to get an insight into attention. And we thought so too. So we had one of these Empatica sensors in the lab, and we figured, maybe EDA is a good possibility. So we started reviewing the literature. So we did a systematic literature review that was published at CHI this year on how people have been using EDA at CHI, and what can we detect from EDA? Does any of that actually speak to attentional states? And we also consulted the psychophysiology literature to see what are the theoretical basis for all this. And we started comparing the works from CHI and the works from psychology, and we were like, oh my God, there's not a very good match here about what people are using EDA for and what the literature actually says that EDA is about. So we did this methodological analysis, and we found papers exploring the use of EDA for a very wide variety of contexts, using for pretty much anything, both with and without support in the literature. We had the feeling that people usually, when they use EDA, and I'm guilty of this as well in the past, so I don't count myself out of this. It's entirely driven by, okay, what are the sensors that we have in the lab? Let's throw everything at it and see what comes out of this, right? Which is fine early on. You're exploring things. A lot of the work that we do in HCI is exploratory in nature, but it comes to a point where you really want to be a bit more controlled in your experiment. So the support for the use of EDA for measuring cognitive load is a bit mixed. So there's not enough evidence to differentiate between lower and higher mental workload, and it may indicate points in a task where cognitive demand increased. So basically, you can tell when something happened, but it's really hard to tell, how much that is, because the EDA has two levels, right? So it tell you there's this high frequency component that is really good at timing things, and you have this low frequency component that is about a level of things, right? So, and cognitive demand seems to be related to those spikes that you see in the data, but not so much about the level. And we have in the paper a bunch of guidelines that we found useful for ourselves, and maybe will also be useful for other researchers that are interested in using EDA for any kind of user measuring. So the takeaways from this work is that gaze data offers a wealth of contextual information about users' attention, activities, and so on. Because eye movements are task dependent, we can go the other way and use gaze data to recognize activities. It also shows potential to recognize other facets of attentional states, especially when combined with other senses. Facial temperature is one modality that shows promise for mental workload estimation, but more work is needed. I don't even fully trust my own results entirely on this. I think that needs a lot more work in really doing this properly. We used very rudimentary computer vision techniques for extracting this information, and it certainly needs more robust mapping and really understanding what are the principles behind this, but it does show promise. We've done a few studies that we use machine learning to try to extract some of this, and it might very well be that this is all overfit, but I do think that it's a modality that offers good potential for this task. Okay, so we understood a bit how attention, how mixed reality changes our attention when we're using AR. We talked a bit about how to measure and sense attentional state. What can we do with this? So I think a really interesting principle about eye movements is that gaze precedes action. So when we're about to pick up something or touch something, our eyes get there first. So if the eyes get there first, it gives us a few milliseconds of notice about what's about to happen. And one of my PhD students, Joshua Noon, he actually did his PhD on intention recognition from eye tracking data. So we ran a series of studies like this. So we used the game Ticket to Ride as our toy example and collected eye tracking data of people playing this game. So this game is about connecting cities. So you have this map and you have to create railroads between cities. And so basically a strategy board game. And we built an intention-aware AI system. So we have an agent that is always trying to predict what the user is going to do next. And you can see here the game progressing, right? So the user is making actions in the game and the agent is monitoring where the user is looking. And you can see through the thickness of the lines on the right, you can see the user, the agent changing its beliefs about where the user is trying to go. So after a while, it's pretty clear what is the player's plan in this game. Now this is in 2x. And you see here on the left, what are the routes that the player actually ends up building, right? And we use this this game as a test bed for designing interactions between intelligent agents that are monitoring attention and players. So a lot of that, because there's a lot of interesting conversational challenge. How can we communicate to someone else that the other player has a certain intention? So we're imagining this scenario where you're playing games together with an AI agent that is there helping you, giving you tips and so on. So there's a really cool project there. And you can see that indeed the AI gets it pretty well in terms of comparing the predictions of the AI and the end game state. So we published this at AMAS, the first model, and later on we had a paper at the AI journal with a full model for this. Another project that is about this relationship between action and gaze behavior is this note-taking system that we built. This is a project of Van and Kam, another one of my PhD students. So the idea here was that imagine that you're reading a piece of text, and as you're reading the text, you're voicing out your thoughts about the text. So instead of stopping, highlighting, taking notes, and kind of interrupting your flow. You're just kind of voicing out your thoughts as you read a paper. So, you know, the academics here in the audience, imagine that you're reading an essay from one of your students and you're giving them feedback, or maybe you're marking something, and without having to take your hands off the device, right? So, and what was interesting, what we wanted to do here is to combine the gaze behavior as you're reading with your voice comments that you're speaking, to automatically attach those voice comments to the passages in the text to which they refer. So the challenge was, given this implicit data set, can we detect the passage to which a certain comment refers to? And we built this into the system called GAVIN, which stands for Gaze-Assisted Voice-Based Implicit Note-Taking. So the idea was, you know, we take that speech audio file, we segment this into the different notes that the user is making. Then we do some OCR into the PDF. We extract the different passages that are possible. Then we basically compute gaze features, because just because you're looking at a piece of text when you're speaking doesn't mean that what you're saying refers to that piece of text, as we found in our analysis. But with some machine learning, you can actually figure out where what it refers. So the idea was, we take gaze, we take the content of what you're saying, we take the content of the stimulus, and together with these, we can actually paint a really complete picture of the relationship between what you say and what you're reading. We published the initial version of this at Tokai, and we have a paper now under review at CHI where so the Tokai article is just about gaze, and the paper under review now also uses the content of the text and the content of the voice to make this mapping. So takeaways, you know, eye movements review what the user's intentions, review users' intentions, both in the short term and in the long term. Both in terms of what you're going to do next, like in the example of mapping voice notes to text, but also in the long term, like the Ticket to Ride strategy example. Eye movements can be integrated with other modalities, such as voice and users' behaviors within the app, and with knowledge of the stimulus, such as the content of the text being read, to enable new experiences. Now, can the knowledge of intention? So far, you know, we demonstrated you can detect context, you can detect intention. Like, can we put this together to actually support users' attention? Can we close the loop? Right? So we're using attention to help users focus their attention, in a sense, right? And this is another piece of work. So this is by Brandon Siem. So this is also under review at CHI at the moment. So we're looking at a mixed reality system for decision making. So we have this murder mystery task with a bunch of post-it notes floating around the space. And we built this agent that is analyzing your gaze behavior, you know, which notes you're reading, what's the sequence of notes that you're touching on. It's monitoring how you're manipulating the notes. And, you know, in this app, you can take these post-it notes, you can place them in these boards. And as you're placing in these boards, it's creating these clusters through unsupervised learning in the background. So at the moment here, once you start placing notes, it starts clustering the next notes to kind of help the user focus their exploration of what they might be looking at next. The user can also set a few notes as irrelevant, and then the system starts hiding some of the notes that the user doesn't want to look at. So again, we're exploring how an AI agent can work in tandem with the user to help them focus their attention. So you see here, the agent already collapsed a few of the notes. The user can go there and click to uncollapse them. And so we see this, the value of this in two ways. So one is by highlighting the notes. So you see this green boundary. Those are the notes that the agent is thinking, okay, we think that this is really relevant to the kinds of things that you've been looking at recently. And the collapsing, which is, I don't think you need to look at these ones, right? And the agent has no knowledge of the task, right? So there's nothing Wizard of Oz here. This is all based on NLP of the notes. You can input any kind of data to the system, and it will try to do its best and uses reinforcement learning to kind of adapt as the user is interacting with the system. And so is it any better? So we compared this with an unassisted augmented reality. So you have everything, but no agent. And we compared this with a pen and paper situation where, you know, you have these physical post-it notes that you're placing around the room. And, you know, so in this plot, we have rate correct score. So the higher, the better. And we found, okay, we built all of this fancy machine learning, fancy augmented reality. Is it any better? Well, maybe. So, but probably not, but maybe. So what did we find? We find that the best performance on average was with paper, but there was no significant difference between these conditions. So this was a study with 60 people, 60 people. So, you know, but between participants, so it's a bit hard to get anything significant there. But what we found is a huge variance in the assisted AR condition. So when you add an agent there, you know, some people do really, really well. Some people do really, really poorly. And started looking into, you know, the footage to see, you know, what is it? What is causing this huge discrepancy here? Because it's much larger than the others. And this is what we found. So these are some of the challenges that we identified for these attentional agents. So even if the agent works well, the user must trust it for it to have a meaningful effect. So the users that trusted the agent, that said, okay, if the agent minimized anything, I'm not going to touch on that again. And if the agent highlighted something, I should look into that, right? So those were the users that did very well. But a lot of the users looked at what the agent was suggesting and said, you know what, no. I know that you collapsed this, but I really want to see what's behind it. And even myself, when I was using the system, I would go like, what was this again? And then you open it again and you end up losing time. So those are the users that did very poorly. So there's a lot of work that I think is exciting in this space. So how can we more explicitly convey our intention to the agent? So we've been talking about how can we detect this implicitly just from the data. But how can we combine this implicit, how can we give direction to the agent? So if the agent makes an inference about what we're trying to do, how can we correct the agent if they're wrong? Or how can we know what the agent thinks my intention is so that I can trust it better? And how can we offer feedback about UI adaptations to the agent on the fly as you're using this? So if the agent is collapsing a bunch of stuff, you can say, you know what, maybe stop this for a second because I really want to take a big picture here. So, you know, there's a lot of interesting interaction design challenges there. So in summary, mixed reality creates interesting attentional challenges, but also exciting opportunities for interfaces driven by users' attention. Though gaze data offers an intuitive pointing mechanism for mixed reality, it offers actually a lot more than that too. Through gaze data, we can estimate attentional states, infer activities, predict intentions, and add meaning to actions performed with other modalities. A challenge for future research lies in how to design and build AI agents that can interpret these data and design interactions with these agents to more effectively support their users. So that was my spiel for today. Thank you very much for listening, and I'm happy to take some questions. We still have a bit of time there. Thank you.
Thank you very much,